Swayam Prabha. Digital India. Educated India.
That is there. So what we have over here is a rectangular beam which has a height h, or the depth is h and the width is b, and subjected to a shear force v over here. Now what I'm trying to do is that I'm trying to derive the expression for the shear stress at any given point. So let's say at a point y, at a distance y from the neutral axis over here. So about this particular line, I'm trying to find that what is the value of tau. So what I'm trying to find is that over here, all along this particular width, what is this value of the tau that is acting. So now for these ones, remember that we have already derived, the formulation stays unchanged. We know that our tau equals to v times q divided by I times t over here. Now let's break down these individual components that are there. So the v is nothing but the applied shear v over here. Now coming to q. Now q is what? Q is the product of the area times the distance of the centroid of the area from the neutral axis. You could take the top area or the bottom one, doesn't matter. So let's just take the top area in this case. So here your q is going to be equals to a prime times y bar prime. Right, so this is a prime times y bar prime, this distance over here. Now if you substitute the expressions, and I'm not going to go into the details of that, it's fairly simple. For example, your a prime is nothing but product of this width and this height over here. So this width is b and this height, if you see, the total height is h over 2. The distance of the neutral axis from this section plane is y, so this is h over 2 minus y. And similarly you can find this y bar prime as well in terms of h over 2 and y over here. So after you substitute these guys over here, and I encourage you to do that if you want to, because it's just simple algebraic manipulations, what you will get eventually for the expression of q is something like this. You will get q as equal to b over 2 h square by 4 minus y square. So that is your q, right? So that takes care of this q guy over here. Now I, remember, I is for the entire section, or for the rectangular section it is very easy to write. For the rectangular section, your I becomes equals to 1 by 12 b, which is the width, times the depth q, 1 by 12 b times h cube that you have over here. And the last thing in this expression is this t. T is, remember, is the width at which you are calculating this tau over here. So this width over here, since it's a rectangular cross section, t is nothing but equals to this b that you have over here, right? So t is equals to your b. So after you substitute all of these guys, that is this guy and this guy, in the formula for tau equals to vq by it, the expression for tau that you get, it boils down to something like this. So this is the expression of tau that we get, right? So if we sort of highlight this expression, what do you see just from an initial glance? What you see over here, that from the nature of the expression itself, it's a quadratic variation. So tau has a parabolic variation across the cross section. So let's make a quick note of that. So tau So it has a parabolic variation, as you can see. Now let's calculate the shear stress tau at different points of interest across the cross section. What can be some of the points of interest? One of the point of interest is that at exactly y equals to 0. So that is at the neutral axis over here. What is the value of tau I would be interested in? And also maybe at the extreme edges, that is at plus h over 2 minus h over 2 over here, what is the value of tau? So let's first calculate a tau at y equals to 0 and then at the extreme edges over here. So first, when you calculate at the neutral axis, what we can write, that tau at the neutral axis, so that means tau at y equals to 0, if you substitute y equals to 0 in this expression, what you essentially get, if you put y equals to 0 over here, this guy goes for a toss. Your h square and this h cube, it cancels out. You have a h here, and then 6 divided by 4 becomes equals to 1.5 or 3 over 2. So you will get the value of tau equals to 1.5 times v divided by b times h, which can be further simplified to 1.5 times v divided by a. Now, this brings us to an important point. What do we know by v divided by a? What is v divided by a? It is simply this shear force that you have over here divided by the b times h. And what did we say that particular terminology is? You're right, it is just the average stress, right? So we had sort of defined in a crude sense that our average stress is the shear force divided by the area. So v divided by a is nothing but the tau average. So now do you get a sense that expression is kind of wrong, because within the cross section you can have regions near the neutral axis where the shear stress can be 1.5 times the average shear stress that you have. So let's maybe quickly make a note of that your v divided by a is nothing but tau average, right? So this expression boils down to, right? So this is at one point of interest at the neutral axis. Now let's see the other points of interest at plus h over 2 and minus h over 2 over here. So if you put that h over 2, you will see this guy becomes 0. So essentially your tau at these edges is equals to 0. So what does this mean? That means that in a rectangular cross section, see how interesting this is, that in a rectangular cross section, at the top and at the bottom over here, the shear stresses are absolutely 0. And it kind of also makes sense. Can you tell why? Because you see, this shear, we had hypothesized, it has a complementary shear in the longitudinal direction, right? Now the top of the beam, there is no force which is acting across the surface, and at the top of the beam you don't have any force acting over here. So that means the complementary shear exactly at the top is going to be 0, and that's how it works out. So at the top and the bottom, since there is no force, no external force over here, the complementary shear must also vanish, so it becomes equals to 0 over here. While at this central point over here, you have 1.5 times v divided by a, and the entire variation is parabolic. So if we just have to sketch the variation of tau across the cross section, how does it look like? Across the cross section, the variation looks like this, where at the top you have tau equals to 0, at the base you have tau equals to 0, and at the center over here you have tau equals to tau max. The highest stresses happen over here, that is 1.5 times v divided by e, right? So this is the variation of the shear stress across this rectangular cross section at the top as well as the bottom. Now remember that this stress which I drew over, it is from elevation. So if you are looking at this from this particular side, so it is 0 across this entire line. At the center it is 1.5 times across this entire. Now let's take a look at this figure in 3D for a better understanding. So it looks something like this over here, right? So here, see, at the top it is 0, and this is the parabolic variation that you are seeing, and at the center it is a max, a tau max, which is over here, which at the neutral axis it is 1.5 times the average shear stress. This is extremely important. So this sort of takes a hit to your concept of the average stress, because within the beam you can have regions where the actual shear stress is actually 1.5 times, several times than the average shear stress that you have, and the tau minimum in this case is 0, which is at the top and at the bottom over here. Now if we, from the perspective of complementarity, if you take a look at the stresses at at this central line over here, it looks something like this. So if here, so and also one more thing before we move on, this figure just shows is at the edges over here, but all throughout it is actually like a 3D kind of a parabola. So all throughout you have this parabolic variation that is there. Now Now remember that in, I think, one of the lectures, one of the introductory lectures, we had said, you see the size of the arrows which are representative of the magnitude. You see the size of the arrows at the center is much bigger than the ones at the edges, and now you know the reason why. Because the size of the arrows are highest here because you have the highest amount of shear stresses here and negligible shear stresses at the very top and at the very bottom, and a parabolic variation throughout. Now coming to that central line over here, because of complementarity, remember at the neutral axis, if this is my tau max over here, I have a complementary, so this is from complementarity, as a result of which you have an equal shear which is going along this longitudinal axis over here. Now I will show you an example where beams, rectangular beams, wooden beams, which are, wood is a material which is not very strong in shear. So for wooden beams, if you go to very old houses, you know, where, or you know, in some of the very old, you know, places of religious worship, that you have these wooden beams and the purlines and the rafters that is there, you may find this kind of a scenario. You may find cases where your crack has sort of propagated at the center. This is a shear crack that you have. So now you know, when you see these beams, that why this crack has happened. It has simply happened. And very interesting thing to note, you see this crack, it propagates along the longitudinal axis. That also gives you that sense of complementarity that is there. At the center, the tau is the maximum, that is this tau max that you have over here, and because of complementarity, this shear sort of propagates across this length of the beam that you have over here, and as a result of which you have sometimes you can have a crack or kind of a failure over here. So in a nutshell, overall, what did we learn for the beams with a rectangular cross section? What we essentially learned was that the maximum shear stress is much higher, that is 1.5 times at the average shear, and it happens at the neutral axis. And since it's a rectangular cross section, neutral axis is exactly at the center. And also one more thing we learned is that you have a zero shear at the top and at the bottom over here, because, and the reason is that, and if you intuitively want to, you know, sort of think about it, that there is no tangential shear load at the top surface or at the bottom surface of the beam. So that means the complementary shear over here must also be equal to 0. Now that we have this, let's do an example problem, not for a completely rectangular section, but some kind of a structure that is, you know, made of individual rectangular pieces. So let's go ahead and take a look. I section, right? So it looks like an eye, that's why it's called an I section. It's not a thin walled I section. You will see later, you know, in this topic we will cover thin walled I sections where the shear stress distribution is completely different than what we are studying until now. So it's not a thin wall. It has sufficient, you know, thin walled in the sense the width of the flange that you see over here. In I sections, I am not sure if you are familiar with the terminology. This top part is known as the flange. This vertical part is known as the web, and again the bottom part is known as the flange. So let me maybe make a note of that. You will find this terminology useful later as well. So this is the flange, this is the web, and this part is the flange again. Right? So what you're given are these different dimensions, that is the, you know, the thickness of the flange, the overall width, which is 300 mm over here, and you have the, you know, the central height, which is given 100. Since it's symmetric, as you can see that your centroid is exactly at the center, that is at the neutral axis, that is at 100 mm over here, right? Now you're also given the I, the area moment of inertia. This is something which you should be able to calculate given all the dimensions of this section. I have not calculated that. You can go ahead and calculate, and you will see you will get this particular number. Now what this problem tells you, that this steel I section, and steel I sections are actually extremely popular for steel constructions in bridges and so on. What this problem says, that here for this steel I section, here it is subjected to a shear force of 80 kilonewtons. So this V is 80, and what this problem asks you is to draw a sketch of the shear stress distribution across this cross section that you have. Now we have derived it for a rectangle, so this is actually something which is, you know, composed of individual parts, that is a rectangle. Now this figure that you see over here is simply the section view of this one. This is the 3D view, this is the section view. So if you're looking from this side, you know, you will see that this is the section, and the dimensions are also marked over here. Now that we have, you know, this figure, what are our, you know, some of the key points of interest? Because we know a few things until now. The few things we know is that for rectangular cross sections, the stress distribution is kind of parabolic that we have, and it is maximum, you know, at the centroid kind of a thing, and at the edges it becomes equals to. So some of the things which we have, you know, sort of derived. Now for this one, what are going to be my points of interest? One point of interest will be the top edge and the bottom edge over here, and there we kind of know it is going to be 0. Another 2 points of interest would be, see at this interface over here, there is a jump. Now remember that in our tau equals to vq divided by it, the denominator, the t, that is the width. So here you see the width undergoes a jump from 300 mm to 15 mm. So this thickness is 15. From 300 it goes a jump, so you can expect the shear stress to go a jump as well. So maybe at this interface over here, let's just mark 2 points, one just above the interface and one just below the interface over here. So let's go ahead and mark that. The bottom point I have marked as B, and just above the interface I have marked as B prime over here. Now these are another 2 points of interest where I can expect a jump to happen, and then there is not much of discontinuity. Another point of interest may be the centroid C that I have over here, that is exactly at the neutral axis. Now since it's a symmetric section, what we can expect that the shear stress distribution, if I start from the top and reach the center, it is going to be a mirror image. The bottom part will be simply a mirror image of that one. Now so let's write the formula for what we had sort of derived, and at these different points of interest, let's try to write the expressions for the tau which we are going to get. So what we can write over here, that our tau, we know that equals to vq divided by I times t. So first is at the very top, at the very bottom, since there is no transverse shear, we know at the top and the bottom it is going to be 0. So let's just make a note of that. So at top, bottom, at the top and the bottom tau is 0. Let's come to our next point of interest. So that is maybe B prime over here. Now in this expression, the V is already given, I is for that entire section which is over here, T is the thickness, the width. So at B prime, which is just above, at B prime you see the width of the section is 300 mm. So at B prime I can write that my T is 300 mm that you have over here. And what about the Q? The Q, again, remember Q is always for the area above or below. Let's consider the area above, it's easier. Now this B is just above the section, so essentially for B prime or B you are going to have the same Q, because this B and B prime are just above and just below this, where this width changes over here. So let's write the expression for Q. So Q, you remember, is the product of the area, that is the area of this part over here. So maybe it's better I probably just mark this area, right? So this area times the distance of the centroid of this area up to the neutral axis. So let's write the expression for that. I will write it, you can verify whether what I'm writing is correct over here. So this is the expression for Q that we get. 300 times 200 is this area, and this y bar prime is the distance from the neutral axis to here. You see this is 100 mm plus this half of this one, because the centroid of this top rectangle will be half of that 20, so it is 110 over here. So at B prime, if you substitute all the values, given that V equals to 80 kilonewtons, I, and you have all the other parameters over here, what you will see that this tau, it comes out as 1.13 MPa. Now let's move to our next point of interest, which is B, which is just below. So the only thing which is going to change, V stays the same, Q stays the same as well, because you're looking at the area above. So if your point B is just below that in that point of intersection, your Q stays the same, I stays the same. So the only thing which changes is this T. From 300 now it becomes 15 mm over here. So let's make a note of that. If you substitute the numbers for this one, you will get the value of tau at B. So you see the increasing jump that you have. The moment you move from B prime to B, your shear stresses essentially shoots up. From 1.13, it goes to this jump of 22.6 MPa. So let's maybe mark these ones over here. So the top one is tau at B prime, and this is the tau at B. Now, last thing which is remaining in our points of interest is the centroid C over here. So for the centroid C, we are going to consider this entire area that is there. You can break up into two individual chunks when you calculate the Q. You can calculate the Q for this one. Remember, we had seen that when we have, you know, cross section which is just not one uniform rectangle, you can calculate the Q for this and for, you know, this bottom part over here. This one, let me mark that as well, and you can, you know, add that up. So it is essentially for this top rectangle, it is a prime y bar prime, and this bottom rectangle a prime y bar prime, and then you add it up to get the total Q. So you can go ahead and do that. So for that, what you will get, the value of Q is so let me just mark that at C. So at C, you get is the value of Q, and again you substitute in the same formulation that is there, that your tau at C at C, we get tau of C as 25.2 MPa. So let's again jot down the main regions we saw. So first at the top and the bottom it is 0. At your B prime it is 1.13 MPa, at B it is 22.6 MPa, and at C it is 25.2 MPa. And we know since these are sections are rectangle, you will have a kind of a parabolic variation that is there. So let us draw the variation across this entire section. So I am going to draw for this section in a 2D diagram from, you know, when I am viewing from, you know, this side over here. So let's see how this variation happens. So at the top here, at the top in this part over here, it is equals to 0. Then at B, which is 1.13, then at B itself, just at B prime, just below B, I am going to have a jump which is going to 22.6, and then at C I will have 25.2. So these are the different ordinates of your shear stress. So at the top is 0, then you come down here, this is your point B prime. At B prime you have 1.13, and just to the below of B prime where you have the point B undergoing a jump, that becomes 22.6. From there you are coming to the centroid of the section C, so that is 25.2. Then again the bottom part is an exact mirror image of what you have at the top. So I hope with this example it is clear that how we derive the shear stress distribution across the entire section. Now remember that these values are not, you know, happening just at the edge, it is happening across this entire section. So this 0 over here is across this entire section, this 1.13 is across this entire section over here, at this C it is across this entire, this small section that you see, that you have 25.2. The next item in our agenda for discussion in the chapter of shear are built up beams or built up sections, which essentially means that beams which are built up of two different sections, not materially different, but maybe two different boards which are sort of glued together, kind of the problem we have seen, or you have put nails together to hold the boards together. These kinds of beams, if you see all around your house, you know, you will probably find your bookshelves maybe, or your dressing table somewhere, you have, you know, these different boards which are glued together or nailed together. So if you see some of these pictures, these are, you know, very common examples. So, you know, so it's a structure built out of multiple parts. So you have, you know, suppose you have this something like this, and you have this glue at these interfaces over here, or you have a bottom board and a top board over here, and then these boards are sort of held together, you know, using these nails that you see. Or you have something like this where you have these, you know, bolts which are holding it together. One another classic example of this are in bridges. You have these girders, and don't be fooled by the depth of these I sections which are there. You can see the total height of a plate girder in a bridge. You will learn more about this if you later take a course on steel design or bridge engineering. The steel girders, so on top you have other members, some two dissimilar materials which are there. This is a case where you have two dissimilar materials and yet is built up. So you have these bolts that you see, they are called rivets. So these bolts are essentially holding those two together. So in a nutshell, these structures are very common. So next time, suppose you have some issue at home and you are supposed to put two of these things together, and you're supposed to put some nails or some glues and so on. So when you're putting the nails, a common question which will arise in your mind is that how many nails should I put, what should be the spacing in between the nails. So this topic essentially addresses that issue, right? Like how these nails effectively resist the shear and how to calculate the spacing of the nails and so on. So now if you remember that this is an example which we did. This was also a built up section where, remember, you had two boards which were this let me mark them to jog your memory. We had this B1 and this guy B2 over here, where at this interface there was this plane of glue. So this is the the plane of glue that was there over here. Now remember that how we solved this problem. In this problem, what we did, we had calculated the maximum shear, so that was 19.5, and from that complementarity, that VQ by IT and so on, we had found that what is the tau which is going on over here. So essentially here, what this glue, the job of the glue was to resist this shear. The job of the glue which is applied along this interface, along the entire length, was to resist the shear force, the longitudinal shear, which is complementary to this vertical shear over here. This tau and this tau, remember, they were complementary shear. Now the question here, so let's make a note. So the glue, the job of the glue was to essentially resist shear. Okay. But now if I come and then tell you that instead of the glue over here, what if I put nails? So now there is no glue. I have removed the glue, or there was no glue to begin with in between these two boards which were your B1 and B2. Now instead of the glue, I have to punch nails. So the nails, the job of the nails is essentially the same. The job of the nails is essentially to resist the shear. But now you see, in between the nails you have gaps. So one nail resists some amount of shear, then there is a gap, there is no glue, there is no more glue. It is just two boards where you have punched the nails over there. So one bolt resists the shear, then the shear travels, and then another bolt. So overall, all the nails together is doing the job which the glue was doing. So the question here, right? So the question here is that what is the spacing in between the nails? How do you know? You can go and punch as many nails as you want, and then what you will do, eventually you will end up spending a lot more money in buying nails. Now for small two boards, the price may not make a difference, but remember that if you are say in charge of a furniture manufacturing company, right? So you have to procure nails and these fasteners. Nails are also called fasteners. These fasteners in bulk. So what is the efficient way to find, or what is going to be the spacing on the nail? So you see, it's a very practical problem that you are dealing with over here. So the question is that how do we find the spacing between the nails, or essentially this quantity S over here, right? So let's take a closer look at the problem and try to find. And in this section, in this topic of the built up sections, we'll come across a new terminology. Well, not new, you have heard of this terminology when we were talking about torsion as well, which is known as shear flow. We will revisit that one and see from the perspective of resisting shear. So let's go ahead, let's move on. So if you see here now, let's see that what's going on. So here also you see you have two boards, and I don't know if it's not very visible over here. You essentially have two boards. So let me mark it. So you have one board which is this is the demarcating plane that you see. So here also you have say board 1 and a board 2, and in the bottom figure here also maybe this is board 1 and board 2. And in both the cases, these boards are held together by these nails that you see over here. Now try to visualize the problem or the system. Now we have hypothesized that along this, we will come to this figure later. We have hypothesized that here at this interface, or at this interface over here, whatever is the tau, right? So here whatever was my tau over here, or in this interface, whatever is the tau is resisted in the longitudinal direction. You cannot see the longitudinal direction here by the tau which is over here, right? Okay, so now what is the force in this longitudinal direction? So now you see each of these bolts, right? So if the spacing between the bolts is s, each bolt, the center to center in between the bolts can be taken that each bolt resists the force which is coming in between that region. So what I'm essentially saying that if we take these bolts and if we draw this part over here, which is also s, because center to center, because the distance between the bolts is, so center to center is also s, say, right? So each bolt, say in this case, this particular bolt that you see over here, it is essentially resisting the shear force which is acting in this region, in that, you know, from the center to center, from the center of between these two bolts to the center of between these two bolts where these black lines are drawn. So each bolt is resisting the shear which is going over there, which is shown over here. This is the, you know, you have one bolt over here, another bolt over here. This is the center to center in between the bolt, something like this over here, right? So each bolt is resisting that amount of shear. And so what is the value of the shear each bolt is resisting? So again, try to visualize that we have this tau which is acting. So let me explicitly write tau over here, right? So the shear force which is acting in this distance s is what? How do we get force? We get force as stress times the area of cross section. So the shear force which is acting is going to be tau times this area, this small rectangular area that you are going to have. It is going to be s times the thickness of this board over here, that is the t, right? So if I have to sort of, make this maybe a bit more messier, it is essentially each bolt is resisting this one. This is s times this guy is t, which is essentially the thickness of the this thing that you have. Let me write the t properly, not to confuse with tau, right? So it is s times t times the tau. This tau, it is the force which is acting over there, right? So let's make a note of that. So force resisted by each bolt is going to be tau times t times s. So this is the force resisted by each bolt. So let me say that as F. Now this figure will make some amount of sense to you. So here we have already said deciphered, this is the S and this is the F over here. Now this Q, what is this guy Q doing over here? And also you may want to think that this is maybe, so if you get if your problem asks you, or if you want to find that what is the the maximum spacing that you can provide, that will of course depend upon the allowable strength, allowable force the bolt can take. So if the bolt cannot take any more, you have to put more closer nails that you have over here. So anyway, keeping that aside, the force resisted by each bolt is this one. Now if I take this guy over here and if I replace by a variable, see if I rewrite that equation and bring F on the other side, so F I can write as equals to a variable Q times S over here, right? Where Q is essentially tau times T. So what does that mean? What is Q? Because I have to multiply Q with S to get the force. So Q is essentially the shear force per unit length. So let's just write that over here. So Q, what I derive, so Q is equals to nothing but tau times T. Right? Now, what do we know about tau? Tau we know is equals to VQ divided by IT. We have seen that already. So that essentially gives you that VQ divided by IT times T. So this T and this T goes for a toss, and eventually what you get is the formula that Q equals to small q equals to VQ divided by I. Right now I have written this just as Q, and this Q is essentially, it is taking part in resisting the total shear V, right? And so that is why, since it's resisting the total shear V, I'm going to write this Q as Q total or Q tot, right? So we will see that why I'm writing it as total, because in some cases you may have two rows of nails. We'll come to that example. So just for the sake of discussion, now let's make this Q as Q total, TOT. Right? So what we derived is a very important relationship over here, and this Q, my friends, is known as the shear flow. So this is, and why is it called a shear flow? It is the shear force per unit length. You see, shear force, if you do F divided by S, so that is the shear force per unit length. So that you see over here. So this is the shear flow which is acting. So you take this Q, you multiply with this S. You take the Q, you multiply with this S, and maybe I can mark this as a total here as well. So you take the Q total, multiply with S, that will give you the shear force which is being resisted by each bolt over here. So this Q is known as the shear flow. Right. So we now know what is this Q total, that is the V times Q, that is the shear flow, or it can also be written as shear force per unit length. Now let's come to some of the other special cases. So now we know how to calculate the force which is coming in each bolt. We calculate the Q as VQ divided by I, right? Now we know how to calculate this already, although we will come to the discussion on how to calculate Q in these cases, times the S. So to calculate the spacing S is nothing but F divided by the Q total in this particular case, right? So now let's come to some of the other examples. Maybe here is that, now what if instead of having just one row of bolts that is there, so you had just one row of bolts, what if you have two rows of bolts? So the problem gets slightly more involved, right? Although it is not, if you think about it. So here you see, here you have one board over here, and the two of the other boards over here. So if you just mark it over here, maybe I can write this is your B1 and this is your B2. So here also, if you just come from the balancing of the forces, from the moments, from where we had derived our expression for the shear, that VQ equals to that tau equals to VQ by IT and so on. See here also, when you're applying the moment, remember that shear, in addition to being transverse, it is also longitudinal. So what will happen here, if you have these kinds of these are the results of the moments that you have, those triangular stress distributions, part of that over there. As a result of that, this board will try to be pushed in this particular direction if you have the shear, because your longitudinal shear is complementary to the transverse shear that you have. And essentially what these bolts are doing, it's keeping everything intact, it is keeping everything in place. So you have two rows of bolts over here. So you see, in this case also, if the total shear force in this particular case, let's say the total shear force which is acting here is still V. Now in this case as well, I can write my Q total as VQ divided by I. This is what we had seen previously, right? So this is what we had seen. Now the only difference between here and the previous one, you see, now instead of having one row of bolt, you have two rows. So this row and this row. So you can imagine this as that this V essentially gets split into V over 2, V over 2 over here. So each row of this bolt in the longitudinal direction, along this longitudinal direction that you have, it resists this complementary V over 2, and this bolt over here also resists the V over 2 over here. So for each row of bolt, I have a Q each. So if each, for the total Q by both the rows, by this row and this row, is resisting the total V over 2 plus V over 2, that is equals to V. So is the total Q. So but for each row of bolt, it resists a value of Q over 2 because it resists a value of V over 2. So if I have to write for each row of bolt now, so let's write that. So for what I will get is correct. So you see, in the previous one, if you compare it, in the previous case where you had just one row of bolt, in that your F, that is the force resisted by each bolt, or the allowable strength of the bolt, however you want to call it, was Q total times S. Whereas when you have now two rows of bolts, it becomes Q over 2, simply because each row of bolt is resisting V over 2 that you have over here. So for each row of bolt you have, so this Q is actually, so this should ideally be written as Q total. right? Or for each row of bolt, we have the QE each, if you want to write it in that way, that Q each is essentially Q total divided by 2, right? So which is essentially substituted over here. So this particular guy over here is nothing but Q of each row of bolt that you have. So Q each times S is equals to S. So this is important to realize when you have one row of bolt, two row of bolt, or three rows of bolt, and so on, right? So this is a similar thing that you see in a similar pattern over here. So if you have your boards made of something like this, see here, the central part is one composite board over here. So this is your B1, and these outer parts is essentially your secondary boards that you have B2, and maybe you have put glue over here. This figure just shows that this interface shear that is acting, that we also saw in the previous pages, that is there, right? Now also now as I said, so Q equals to VQ by I, so we have already seen this is the total Q again. So again, let's make a note of this. So this is important to realize that the total Q which resisting the total shear equals to VQ by I. Now this is again brings back when you have, instead of one row, you have two rows of bolt or three rows of bolt that is there. So you see here, you have one row of bolt, so your Q each is going to be equals to Q total. So it is nothing but equals to, in this particular case, Q is equals to Q total, right? Where you have two rows of bolts now, then each of them becomes Q over 2 or Q total over 2. Right? That is, we can write Q each equals to Q total over 2. When you have three rows of bolts, it becomes Q over 3. So it becomes Q each equals to Q total over 3. So I hope this idea is clear. So more the number of rows you have, each row has to resist lesser amount of shear. So the total Q gets segregated into Q by the number of rows that you have over there. Then okay. All right. So now one of the questions is that, let me maybe just go back to the previous one, that here you see one of the important things here is that in this formulation, this V is fine. This is the total shear force that is acting across the section that is here. So the across is the entire section V, or across is the entire section V. I is always for this entire cross section, not a part of it, but the entire cross section. Now again, the question is that how do I calculate the Q? When you're talking about built up section, should I take the Q for this entire thing for here, or just this board, or just this part over here? I don't know. Where do I calculate the Q? Now remember that these nails, right, these nails, what you see over here, are essentially resisting the shear of the part which is being slided off. So here this nail is resisting the shear which is acting across this entire board, because this entire board is supposed to be sliding off because of the longitudinal complementary shear. Here this board, this in between, this dark board that you see over here, it is resisting the shear which is trying to slide off this portion, this entire portion. So this, in this case, you have to calculate Q, you should ideally be considering this one, because this is the Q which goes into the amount of shear which is acting on that particular board. Here also, see, these three boards are resisting the shear which is trying to slide off this board. So you have to be a bit judicious and careful of the Q of which part you are computing. So let's take a slightly closer look at that how to consider, or which area to consider for Q over here. Sorry, this here my camera overlays over here, but this is the word concept. So which area to consider for Q? So the rule of thumb is that you find the loose part of the built up section which is likely to be sheared off. So you find the part which is loose, which is likely to be sheared off, right? So you calculate the Q for that loose part over here. The easiest way to do that is that you take a section, right, and you hold the section just below the neutral axis that is there. So what I'm trying to say is that here you come and you maybe put a let me move that slightly up. Okay. You put a board or something over there, and then you try to push that section aside. So it may become more clearer in this one over here, that you locate the neutral axis, you fix the structure below the neutral axis. So let's say that here for any one of the boards, if I want to do, say for this one, say in this particular case over here, the neutral axis may be somewhere here. So I am trying to fix the structure below the neutral axis. So let me draw this, a fixity kind of a thing. So I am fixing the structure below the neutral axis. Now apply a push to the cross section. So for this entire cross section, you apply a push. See which part is about to slide or shear off. So you see over here, suppose these nails were not there. Now I am trying to find the Q for the area first without assuming that the nails are there. So here you see this is made of two boards again. So here let's say here this is my board 1. See, this is the interface where this whole board 1 is, right? And say the bottom parts are the boards 2. Okay. So if these nails are not there, if I fix it and if I try to push this section, which is the area which is about to slide or shear off, this is the part, the B1 is supposed to be to slide or shear off over here. So you are essentially going to calculate the Q for this entire area. So these nails that you have over here are resisting the shear which is acting over that area which is supposed to be sheared off or slided off. So coming to a similar concept for the other ones, in the first figure it is going to be this area over here. See, in the second one, if you hold it over here, if you try to push it, see, this is where the bolts are. The area which is going to try to get sheared off is this entire thing. The third one we already did. In this one, you see in this one there is one board over here and the two other boards. So if you are trying to slide it off, the Q you are going to have to calculate is just for this particular board over here, and the last one is for this particular board over here. So I hope that overall this discussion is clear that how to calculate the Q, or for which area to consider to calculate the Q. And then remember that my small q total is equals to V times capital Q divided by I, and it also depends upon the number of rows of the boards which are there. So let's do a couple of problem examples to reinforce some of these ideas and get our minds clarified of the concept of the shear in built up sections. So this is the first problem example on the built up section. So let's see what the problem says. So you have a wooden built up box beam. So it's a box beam that you see because it looks like a box. So you have two different boards. You have this board over here, this board over here, and two vertical boards, and all of them are fastened with these fasteners which are the nails over here. You are given the allowable shear force in each nail. So in each nail can take up to 800 newtons, not more than that. Beyond that the nails will fail, right? So what you're supposed to find is the permissible nail spacing. So that is this S. So this is the cross section view, and this is the side view. Side view means if you're looking from here. So this is a continuous board, right? So if you have a continuous board, when you're looking from here, this is a nail, and behind that there is a nail, behind that there is a nail. So these are the different nails that you're looking at when you're looking from the side view. And it says that the applied shear force, so this entire cross section is subjected to a shear force of 10.5 kilonewtons. So how do we do this problem? Now, before we start writing it down, we have to find, that we know that the Q is, F times or Q times S equals to F, and that will give us the spacing that is there. So let's just write the basic formula first, and let's see. So in this example, we'll do a little bit more in details in finding out the different parameters, so the idea is clear to you, right? So let's first write our basic generic formula that we have, that my Q, I know that at Q total, right, equals to V times Q divided by I. So this is the total Q, which is resistance. Let's just consider the top one over here, the total Q, that is total V, the total the small q total. So that is the total resisting the total V which is acting over there, right? Okay, so now if you see in this formulation, there are two parameters again which are of interest over here. One of them is this guy Q, which you see, right, and the other one is I. So let's just calculate the Q first. Now remember that we had discussed that for which area should you calculate the Q. So you hold the section below the neutral axis, you just fix it to apply a shear, and then when you apply this one at the shear, you will see that this is the area which is trying to get sheared off, and essentially the nails are provided to prevent shearing of that area. So the area for which we have to calculate the Q is essentially this area that is over here. So let's just calculate the Q for that. So the Q for that is going to be your Q is, remember, it is always, the formula is the same, A prime times Y bar prime. So in this case, my A prime is this area over here, which is 180 times this depth, that is 40 mm. So that is 180 times 40, right? So this is my A prime, times Y bar prime is the distance of the centroid of this area from the neutral axis, which is also given 120. The total board is 40. So up to this central line, you see it is given 120 mm. So it is going to be times 120. So if you plug in the numbers in your calculator and you calculate it, you will get it as 864,000 your meter cube. So that is, remember, the q, the unit of q is the length times q. Okay, now the other thing which to compute in this formula that you see is this denominator I over here. Now I, remember, is for the entire section. So I, for this entire section, it's a scooped out rectangle that you have, so that will be the, for the whole solid one minus this guy over here. So I'm just going to write it out, so in case you're unclear how to calculate the I, you will know that as well. So I for the entire thing is 1 by 12 times B, which is 180 plus 15, which is 210. So 1 by 12 times 210 times D cube, that is 280. So that is assuming that the entire thing is solid. From that we have to subtract the area moment of inertia of this hollow portion that is there. So minus 1 by 12 times the depth of this hollow portion is 200, total is 280 minus 40 top and below. So times sorry, it will be 180 times 200 cube. So 100 times 180 times 200 cube. So that will give you, I have this number calculated already, 264.2 times 10 raised to 6. You can calculate this one at your ease. Mm raised to 4. The unit of area moment of inertia is length raised to 4. Okay. So now that we have these quantities over here, let's calculate the Q total. So the Q total is going to be what? So the Q total will be equals to, the V is given 10.5. So it is 10.5 times 10 cube. I'm calculating in your Newton and mm and so on, times the Q that we calculated, which is this guy over here, divide, I'm just not writing the numbers, divided by I, which is this guy over here. Now if you plug that in, you will get the Q total comes out as 34.3 Newton per mm. Why is it Newton per mm? Remember that Q is your tau times T. So tau is Newton per mm square, T is mm, so 1 mm cancels out, so it is Newton per mm. So the unit for shear flow Q, right, is force per unit length. Okay, so now this is the total Q. Now how many rows of bolts are there? There are 2 rows of bolts, as you see over here, 2 rows of bolts. So that means Q for each row of bolt is going to be what? That is going to be Q total divided by 2. So Q for each, if we have to write it, is Q total divided by 2, right? Now that we have this one, we are going to find the spacing in between the bolts. How do we find that? You remember that Q times each times S, the spacing, equals to the force resisted by the bolt, that is F. Now the maximum force resisted by the bolts here is 800 Newton. So let's write the expression first, that Q each times the spacing S equals to F. Right? So if you plug in the values over here, see here, this is known from the previous line. F is known. F is the maximum force your each bolt can take. So F is essentially, this guy is 800 Newton. So the only thing which are missing here is S. So if you plug in the numbers over here, this will eventually give you that the spacing in between the bolts, that is S, comes out as 46.6. So I hope this problem example was clear, in which we took the total shear, we calculated the total small q, that is Q total. Now we have 2 rows of bolts, we divided that by 2, and from that we calculated the spacing.